Uh, Hello, everyone. I'm Liwei and from CCRG, and today I'm going to talk about SphericalN. So instead of using a really complicated multi-patch system, we are just using one whole spherical patch. Why we will consider spherical coordinates, one of the reasons is because it can take advantage of the approximate symmetries in a number of astrophysical cases, like a single star, single black hole, accretion disks, or also might be the remnant of binary mergers. And it also have lower numerical dissipation in the evolution of fluid angular momentum. So we use Einstein Toolkit. So in order to implement the spherical coordinate in the Einstein Toolkit, first we need to identify the normal Cartesian coordinate x, y, z, and with r, theta, phi, and apply the appropriate internal boundary conditions at the origin, at theta, other poles, and also the phi equals 0 and 2 pi phases. So here's a snapshot. How can you imagine? How can you construct spherical coordinate from the Cartesian coordinate? As you can see, this is the original Cartesian grid, and so this is R, and this is phi, and this is theta direction. So because r equals 0, here is a plane, but in spherical coordinate it's a point. So first we identify this line and identify this line with this line, and you will have a shape like this. Then next, because this is phi equals 0 and this phi equals 2 pi, then you identify these two faces. They will have a cylinder which r equals 0 is a line, but we need to do more. We need to identify this line because it's r equals 0, it's just a point. So it will, when you're trying to shrink this line, then the whole coordinate will, and the whole grid structure will look like this. And this is theta equals 0, and this is theta equals pi. And you keep doing this, then it will finally, you need to, because this cylinder is phi equals 0, it's actually just a line. When you identify the whole cylinder in a line, it will be construct the whole spherical coordinate. Well, there are also some problem with spherical coordinate. The first one is it has the coordinate singularities. All right. But thanks to these papers, we now know how to handle coordinate singularities analytically. We use this so-called reference metric formulations. Suppose you have two tensor Hij, and instead of using the original spherical basis, coordinate basis, you choose orthogonal basis and expand these tensors using this basis instead of the original spherical coordinate basis. Then the component you have, which will be evolving in the numerical grid, will be finite. And similar with these derivative quantities, you can also represent into the use the orthogonal basis. Here's an example for the GRMHD equation. And after doing the reference metric formulation, it looks like this. And all these quantities are finite. And you can just using the normal finite volume method to construct this derivative operators and construct the right hand side and evolve. So another problem with the spherical coordinate is because when you're going close to the origin and the poles, the grid size becomes smaller and smaller. And here's the expression of the dt and the dt you can use because of the CF of condition in the spherical coordinate. As you can see, if you going close to the origin and the poles, then the dt can be very small. So there are a bunch of methods we can use to cure this problem. Just as the previous talk mentioned, we can use this multi-patch system to get rid of these poles and origin. But here we choose a different method, which we use this FFT filter to dampen this unstable mode to increase the time step. In order to do that, we need to filter both in the theta and the phi direction. But because theta is only from 0 to pi and it's not a periodic, first we need to do is we need to do a double covering. So this is the original field. We extended to from 0 to pi to also to pi to 2 pi. Then this function will be periodic, and we can using the FFT to project it to the to the mode space and throw out those higher unstable mode, and using inverse FFT to project back to the physical space. And we can do similar operation to the phi direction. Because in order to do a FFT, you basically need the whole data in a complete theta or phi ring. So it's actually a global communication. So before we apply this filtering, first what we need to do is to collect data and from different MPIs. So in order to make, so first we define, this is the left is the whole data pack, and first we first define the communicators in our direction, and because they are independent with each other, and we can, and inside each communicate R, we can define two types of communicators, R theta and R phi, and use those communicators to collect data when we trying to filter in theta and phi. So here's the scaling test of the filter, and the top panel is iteration per hour, and the green one is without filter, and the blue one is with filter. And as you can see, by apply the filter, the iteration per hour do get a little bit small, and it becomes a little bit slower. However, because of using this filter, we can use much larger time step. So if we look at the physical time per hour, then the line with filter is much larger compared to the without filter case. And okay, so in order to test the code, we first run a vacuum black hole case, which is the spinning boson-York black hole. So here's a two plot of the cipher, L equals 7 and L equals 8. And as you can see, it can capture this mode quite well. And this different, the three different color represent three different, two different resolution. So the red one is the reference one. So for this case, in order to test the limit of the code, we turn the spinning axis not aligned with the axis of the grid. Actually, we turn it to the XY plane, and these are the blue the cases and the blue and green. And for the red one, we align this spinning axis with the axis of the coordinate. So we use this red one as a reference. And as you can see, as we increase the resolution and these two different modes converges to the reference result. Then we tested the GRMHD part of the code. So in this case, this is the spherical explosion. Basically, we put the overbalanced region of radius r equals 1, and we put the center of this sphere off center by 1, I guess, and this is, as you can see, that then it expands. As you can see, that this is the basically the shock. It can go through the origin, and it can go through the origin, and without. But even though it has some small artifact still along the axis. Here's the XZ plane, and here's the same simulation, but on the YZ plane. So next test is the so-called bar mode unstable Tungsten neutron star, and it's we are trying to mimic the final stage of, say, binary neutron stars mergers. Here, what I showed is on the left is the magnetic field, and on the right is the density, and this is the XY plane, and initially it initialized with a toroidal magnetic field, and this is before the onset of the bar mode, and now it's the maximum bar mode shows. As you can see, the spiral arms, and this is after the bar mode stage, and going back to the asymptotic spherical the stage, and it's surrounded by this B field disks, and so as you can see, the code can capture these features quite well, and then here's the same simulation, but on the XZ plane. Yeah, at same time step. All right. So we are also considering because we have new driver now, capital X. We are also considering transplant our SphericalN code from capital X, and because the MREX already have this map structure which can automatically treat Cartesian grid into a spherical coordinate, and and what we also want to do is doing AMR in the, because the capability of MREX, we can try AMR in this way, which we only refine in one direction instead of all the directions, and trying to make the, because there's a lot of trying to kill the small cell problem near the origin and the pulse. Yes, that's pretty much it. Thank you.
And for questions, hi, thank you for the talk. I'm not sure if you've said it and I missed it. Maybe did you try different filtering functions in the FFT and then the inverse FFT and compared their impact? This, I think,
yes.
when you cut off the higher order modes.
Yes. So for the smooth function, say the metric, we use what call, so exponential filter, which we don't touch the base mode if the solution is smooth, but we also need to filter the hydro quantities. There might be shocks, and if we use a different type for the hydro variables, and we use this Gaussian filter. And because if you're still using the exponential filter for the hydro quantities, then it will introduce Gibbs phenomena. And yeah, we do use different type of filter for different type of evolution variables.
Okay. Any other questions?
When you filter the fluid variables, do you use the conservative or the primitive variables?
Conservative.
Okay.
And then you recover the primitives from those filtered and.
Yes.
Yeah.
There's questions online.
Oh,
okay.
Yeah, hey Liwei, can you hear me okay? Just double check.
Yes.
Excellent. Oh, wonderful talk. Really a tour de force. A couple questions. So first, are there any plans to create, let's say, a cylindrical NR code?
No, but
Second question. Let's see. Oh yes, and so there, you said there's a plan to make this work within CarpetX.
yes.
What's the current status of that?
So we are trying to, because this functionality already there, but we we haven't tested. So the first step will be tested with a really small mode like a wave equation and trying to see how, yeah.
Wow.
So-
So what you're saying is pure spherical grids support is there already in
Yes,
Carpet?
yes,
That
yes,
is wonderful. Oh, great.
yes.
Great to know. Thanks very much. Again, great talk.
Perfect. Thank you.
We have time for more questions. Vasily?
So with that, AMRX has the opportunity to do anisotropic measurement.
Yes,
Okay,
yes,
so they can do stuff like that.
yes,
Okay,
but on testing.
not tested.
So yeah, so we need to, if we have problem, we talk to them, they will fix it.
Okay,
It has this capability already.
wait, only refine in one direction,
Yeah.
but not the other.
Yes.
All right, all right. Might be back in business then.
Okay. Good to know. Good to know.
I have one question too. So in my talk, I showed the blast
Yes.
way. It was a shock tube, Cartesian shock tube, slab symmetric.
Yeah.
Going through the origin and with a Cartesian patch that maps
Yes.
the fact. But I forgot to mention your work, of course. I'm sorry, SphericalN can do that in spherical coordinates, fine. Is it just out of the box using the reference metric? That fixes the issue, or is it the filtering that allows you to do this? To propagate shock waves through the origin.
I think
For
it's a
both.
combination of two. Fundamentally, the problem is that the radial phase has zero size at the origin, right? So a purely radial flow will have to be converted into angular flow to get past the origin.
Right.
And it comes back on the other side and then
Right.
flows past. In hydro, you don't really see any artifacts. You have to be a bit careful with the filter in order to, because you need the flow to get around, you cannot really filter with such low effective mode at the origin, then you cannot pass the velocity around. Right? But in hydro, it just goes through and you don't see any evidence of the origin afterwards. MHD is much more tricky. So then I don't have seen anyone who has done that test in spherical coordinates without any problems. But in accretion disk, you wouldn't have any shocks flowing through the axis either, right? So it's kind of like pick your poise and use the coordinate system that was adapted. And
Well, I mean, across the axis, you could have waves that traverse it. That are colloidal. But you could have, I mean, the funnel edge could sweep through it if you have a warp disk or something. It's interesting because all my experiments with harm, I couldn't get it different sizes of the grid there, and I couldn't get it to work with just spherical coordinates in hydro. You said out of the box, hydro is fine with the blast wave.
hydro is fine.
Otherwise,
Mechanically,
you're
you
wrong.
have to do something special about the components of the reconstructed EMFs.
Yeah.
Otherwise, you get some magnetic field that gets thinned on the origin, and then impedes the easy flow through. But hydro is fine.
Okay.
And just go through and you hardly see any effect.
Okay, great. Are there any more questions? Not, let's thank the speaker again.
Not sharing.
Oh, yeah, it's not sharing.
And I'm going to share.
And to get it to go into presentation mode. 5. Pitches. Yeah, I would just press the F5 like I'm supposed to, right? And it doesn't do it.
There's a little icon in the bottom right. What's that? A little to the left too.
This one?
That one right there.
Yeah, all right, there we go. Okay, so here is this. I was asked to give sort of a basic introductory talk to task-based parallelism. So for some of you, this will be nothing new. It can be just like a an intro to computer science talk. I have my image for the task-based parallelism. I took an unauthorized copy from Disney's Fantasia with the brooms going crazy. So hopefully that doesn't get into any copyright problems. Task-based parallelism, I mean, was the title I was asked to use, but I think the normal term is concurrency. Just a little bit of jargon. So parallelism is when you're doing a bunch of the same things at the same time, which is what most of us do when we're doing making use of the cores on a computer. Is we're doing some kind of data parallelism. We've got a loop, and we're running that in parallel with a parallel for. Concurrency is usually like unrelated parallel tasks with overlapping execution. And this is usually achieved in C++ with the standard async and standard future features, if you're familiar with those. I'm going to show you a little bit more about them in a minute. So concurrency and task-based parallelism are kind of the same thing. So the idea here is that with async, we launch a task into the background, and then a future is a proxy for a value. So we say a future is the type of a box, and we give the box a type like an int, and it's just a placeholder for where the result goes when it's ready. And the idea behind using this kind of parallelism is, this kind of parallelism is to reduce the idle cycles that we might otherwise have. So here's how a simple code using asynchrony might look, and it's the classic example of Fibonacci, which is implemented in, I think, the most inefficient way possible. And the use of parallelism makes it even startlingly more inefficient than it normally would be. This is going to give you like order n squared work plus all the parallel overheads for doing almost every instruction. But if you do this right, of course, it's an order 1 calculation. But anyway, so the idea is I'm going to calculate fib of n-1 and fib of n-2. And I launch fib -1 in the background using the async function. And then without using a future, without using an async, I just sort of in the same thread, I compute fib n-2. And then when I want to do the return, I call f1.get, which is going to block until the value is ready. And then I will combine that with fib2 and return the result. And so in this way, what I've done is I've overlapped the computation of fib n-1 and fib n-2. And you can just, you can see how simple that is to code basically, and you can just scale that up in any way you want and overlap various tasks in any way you like. And if you do a bunch of these things, you have a bunch of different futures that cascade into one another. You can get a big dependency graph that's executing in parallel. And this usually goes by the name data flow. And compilers try to generate data flow graphs under the hood for your calculations and make use of that without necessarily worrying you about it under the hood. Stop me at any time if you have a question. This talk is probably not going to use the whole time, so we'll probably get a long break this morning. Okay. So how does this kind of concurrency work? So implicit in the notion of the async future paradigm are a bunch of parallel workers. And a worker is a task that runs on each of the cores of your computer. And it's going to have a list of functions that it can just call, functions that take no arguments and return no values. That just pull one off the stack and do it one after the other. And any kind of call to async deposits a task of this form into that one of those worker queues. And as long as a worker has tasks in its queues, it runs them. But then there's the problem of, what does it do when it runs out? So when it does that, it tries to steal work from other workers on the same machine. Alternatively, there are a couple of strategies whereby, full queues can try to distribute tasks just willy-nilly to other workers. But in any event, there are underlying mechanisms in place to try to keep the workload even between the various workers on the system. And the idea is, if you've got all this working the way you want, right? If this infrastructure is done well, that means that you don't have to worry about how many cores you actually have and dividing work up. The system can sort of handle any number of tasks and will just do them as fast as it can. So challenges of concurrency are numerous. Checkpointing is hard if you don't know what tasks are in flight. There are all kinds of papers on various ways to do checkpointing for large concurrent systems of this nature. The debugging is more difficult without a proper stack. So you're used to seeing, you get some kind of error and you get a stack trace and you say, oh yeah, I see how I got to that point and what went wrong. Very often when you've got a bunch of different tasks you've started asynchronously, you can't even tell how one task got into the queue or why it's there. So that can be very hard. Race conditions are the worst thing ever. So if you've done any parallel programming at all, you will probably have encountered race conditions, unless, what you've done is OMP parallel 4. You probably never encountered a race condition that way. I mean, you can, but it's much harder. And the problem with race conditions, they can happen like one time in a million. So you can run your code, it could, run for a week, and then the problem would occur. It might be something that happens all the time, but if you stick a print statement in there, it changes the timing and suddenly it doesn't happen at all, right? So I had a story idea. You have an unstoppable, it's kind of like War of the Worlds, right? Where the aliens attack and we can't stop them, but but ordinary virus kills them all. Well, we have a killer AI machines that all die because of a race condition in their code. What do you think of that? All right. So the problem is with most programming languages is that variables are shared by default, and global mutable state is shared by default, and this is also bad because it's hard to tell what changed what in what order. So what you want to do is you want to factor your code into linearizable pieces that you can reason about individually without having to, figure out how things happened in a funny order. This is very difficult to do. And as I said, bugs can manifest once in a million and so forth. There are various techniques to prevent race conditions. Rust guarantees that you will be free of low-level race conditions if you don't use the unsafe constructs and you program carefully. Probably you don't want to learn Rust and switch all your codes over to Rust. C++ will probably gain the ability to do a similar kind of thing with a feature called profiles, which will be something that you can load and limit what your code can do. I'm kind of hoping that we can just wait and that this feature will arrive and we can make all our codes thread safe. But who knows, right? Yes.
So our race conditions, they're not going to stop a program, aren't they? Like they're just bugs.
Well, it depends on how they manifest, right? So if you have two threads that are updating an integer at the same time, then the race condition will manifest as a wrong value, right? But if you have some kind of pointer that you're updating, you might get a null pointer exception or something, and it might kill your code. I mean, there's no limit to the kinds of things it can do. But I'm hoping that, you know, in time we'll get better tools for preventing them. Detecting them isn't, in my opinion, isn't quite as good as preventing them. But anyway, hopefully we'll be able to do that. So distributed concurrency, when one wants to try to take this paradigm up to a distributed system, which is what we all program on, there are a couple of different ways of handling that. One is called the actor model, and an actor it's kind of a nice concept, right? It's a worker that lives in a distributed machine, and instead of being anonymous like we would typically have with the async future paradigm, the actors have identities, and we can send tasks to them. So I can say, hey, I want to run this task on that node over there, and you can do it that way. And if the actor wants to return a value, it has to return a future or a callback of some kind, and not direct values, because that's just not the way the paradigm works. Now, there's a programming framework out there called Charm++. It's been out there, I don't know, over 20 years, that is based on the actor model. And instead of work stealing, what they have is a migration. So they divide the work up between these various actors, and then periodically they go in and analyze the load. And if it's imbalanced, they try to redistribute the actors so that the calculation works better. And they've had a lot of success with this. There's another project called HPX, which is based at LSU. And this is their T-shirt, the Stellar Group T-shirt, which provides HPX. They provide a distributed task execution model that's similar to the actor model. It doesn't strictly work the same way. So an actor is going to do a single thing at a time, right? It's going to have a queue, and you can put things onto that queue, and the actor will do one thing at a time off that queue. HPX doesn't quite provide something similar to that. It's more of a willy-nilly approach to when the tasks arrive and when they get done. They can overlap and so on. Whether you think that's better or worse is up to you, and depends on what you're doing, I suppose. But in any event, these are two of the popular frameworks that are out there for doing this kind of high-level distributed tasks. There are multiple frameworks. If you go out, it's like anything these days, right? If you go out and you start searching for these kinds of asynchronous many task systems that work on a distributed system, you can probably find a few dozen of them, right? So these are two that I am familiar with, and there are many others. So blocking functions are a potentially bad thing. They reduce parallelism by forcing workers to be idle. HPX, instead of having just a future.get function, which is going to block, right, has a future.then function, which will queue up that second function to run after the future compiles, and this is after the future completes. And that's better than blocking, because it doesn't cause a worker to become idle. HPX can also use coroutines to swap out block tasks. So in HPX, if you use a mutex, for example, and you lock something, instead of having that worker just taken out of production, instead of that worker just going on a coffee break and not coming back until the lock is unlocked, you can swap that out. You can swap out the work that worker is doing with something else. And so that mitigates the damage of blocking. But it does it, at a cost of overhead. And similarly, C++20 has a co-await function, which does something similar. I mean, if you're a programmer, it looks kind of like calling get on the future, if you call co-await. But under the hood, it's doing something different. It's doing a continuation of the function instead of blocking it, which means you can waste fewer cycles. So when you use these various kinds of code, in many circumstances, you'll be tempted to use. Yes, do you have a question?
Yeah, but it's very technical.
Okay.
I thought HPX actually had its mini task scheduler. So if I was to do a get on the future that is ready, pause my task and yield my resources to another waiting task.
Yes, that's what I'm saying. It does that same that's the same thing that happens with mutexes. Anytime HPX blocks, it can actually swap it out.
Okay.
The default runtime won't do that.
Because the futures then is in fact big, it's true, because I just as well blocking weight, yield my time, come back once.
Yes. Yes, you're right. Your overheads will be different though, right? So so if you use the then function, you'll get, if you use then, you should encounter fewer overheads than if you use get and you count on the task switching to happen.
Okay, thank you.
So, okay. So mutexes are bad for two reasons. One is that they block, right? And this is somewhat mitigated, as I said, if you use HPX for your many task system. But the other thing is they aren't composable, right? So if you look at a piece of code in isolation that uses mutexes, you can't tell how it will affect the whole system. In principle, you have to know what everything is doing in order to know whether your mutexes are going to block. There are ways, if you code carefully, that you can avoid this kind of problem, but it's quite insidious. And anybody who does any large-scale programming with mutexes winds up puzzled over how they got something blocking. There was I saw this paper that said that MySQL has this tasking system where they launch various tasks and they weren't able to figure out why things were locking up. So if the task runs beyond a certain number of seconds, they just automatically kill it. And that's how they run their system. So it's quite a serious problem to work with mutexes, primarily for the second reason is that you can't reason about them without knowing what the whole code is doing. Fortunately, there are other options, right? Instead of using a mutex, you can use a queue, and I won't go into how to make that transition with everything, but you can essentially just say, you can think of it this way, you can say, if I want something, if I want something to only be accessed by a single thread, then I can say only this worker can do that task, right? And if I limit that to a single work queue, then I get the same effect as a mutex. I can't have two things doing it at the same time. And if you're a Java programmer, you'll find that that's sort of the option for the graphics system. You have the event dispatch queue, and if you want to update the graphics, you have to run in that, and that prevents things from overlapping when they shouldn't. In principle, right, a safe access doing a mutex looks like this. You lock, you do stuff, and you unlock, and you want to make sure that do stuff is very small, and that you don't ever do things like accept a pointer to a function and run it in there. Or use something that has an overloaded operator that you don't know what it does in there. And if you're very careful to make sure that you know everything that runs in here and that it's small, and in principle, you can use mutexes safely, but they still block. Okay. So concurrent queues are a nice mechanism, alternative mechanism to use. Yes?
Why would you want to use operator overloading inside?
Why would you want to use operator overloading? Oh, I'm just saying that because C++ has operator overload. Okay, so the question was, why do I want to use operator overloading? I don't. What I'm saying is that because C++ has operator overloading, you might be running an arbitrary function when you don't realize that you're doing it, right? Because you've accepted some kind of argument there, and ++ gets called, and you're thinking of it as just adding it to an integer. But in reality, it's calling some function that's writing to disk and opening a socket and who knows what else.
Right, but the point was the pointer. If I call a pointer to a function by reference and not by value, wouldn't it reduce the compile time? Wouldn't it make it more efficient? You said you don't want to use pointers to a function.
No, the point is, if I run if do stuff contains code that I haven't specifically analyzed to know that it's going to not cause problems with my mutexes, right? Like maybe that code that I'm calling is calling that same lock function in a non-reentrant way. If I don't know exactly what that function is doing, that do stuff, then I'm going to be in trouble. And that's all I'm trying to say is you have to know exactly what's going on in there. You can't allow code that isn't part of your analysis to come in there. Otherwise, you get into this problem with mutexes, right? They're not composable. You can't figure out whether it's safe in general.
Right, but so basically we're avoiding abstraction.
Yeah, you could put it that way. You want to avoid certain abstractions if you're going to use mutexes in a so-called safe way. Yep. And C++ doesn't have a concurrent Q class for you to use just out of the box. I mean, you can write them, they're not terribly difficult. HPX has several, and you can optimize those kinds of queues in various ways, whether you have a single reader, a single writer, or both of those are single. There are different optimizations that you can do to the queue. So I guess what I want to say is parallelism is considered harmful, right? I mean, or concurrency rather. Race conditions and deadlocks can really ruin your life. But the more you can separate the parallel logic, the physics, and the algorithms from each other, the better off you're going to be. And the less reasoning you need to do about parallelism, the better. You want to leave it all to somebody like Hartmut or Eric or somebody who's building a framework for you, if you can, right? So you want some kind of way to abstract it away as much as possible, because you can spend an arbitrary amount of time debugging those kinds of problems. So asynchronous tasks can provide additional parallelism. They can reduce idle cycles, but they can also result in lost brain cycles, lost developer time. It's hard, and you want to keep it from infecting all your code to the extent that you can. You want to have someone else think about it to the extent that you can, but your mileage may vary. All right, so that's it. Any questions? Roland.
So when you go with path-based parallelism, one way that I'm always a bit concerned about is that you might run out of recursive memory or not by having many tasks queued up and not getting done with them quickly enough. Are there any mechanisms in these frameworks that would kind of pause accepting new tasks if they find they're running out of whatnot?
So this is a problem, and it does occur. There are various people who have built mechanisms to fight against that. I don't recall what they are at the top of my head. I know Kathy Yellick has worked on, that's one of the problems she worries about a lot with her task parallelism frameworks. But yes, that is a concern, and you do have to worry about it sometimes. On the other hand, there are many codes that simply don't encounter that problem, depending on how the parallelism happens to fall. Okay. Another question.
There's Zach has one online.
Okay. Yes, Zach.
Hey, Steve. Yeah, great talk. So some ideas popped into my head during your talk, and of course, one of the core drivers for and motivations for writing these asynchronous I/O kind of infrastructures like HPX is the ability to, for example, work on have let's say farm out certain tasks to GPUs, certain tasks for CPUs. Would be great for heterogeneous hardware architectures. I'm really curious to know, do you think it might be able to support heterogeneous software architectures? And by that I mean, let's say, looking into my crystal ball at the future of numerical relativity, right? We might want to say mix an Amrex evolution. Maybe we'll do Amrex for the space-time, and we use another code for the hydrodynamics. Could HPX potentially be used to sort of moderate and distribute the tasks appropriately between, say, two different infrastructures, software infrastructures, I mean?
Speaking sort of theoretically, I think it's possible. I think that the way you would have to do that is either you use HPX or whatever other test framework, and you would modify Amrex to use that. And if you had both of Amrex and your other Hydro code using that same task-based framework, it should be able to coordinate things for them. So I think that should be possible. In,
Yeah,
in,
yeah.
in the,
Mhm.
in the imagined good future where the,
Right, yes,
where the
yes.
brooms don't run amok.
I know. Yeah, I mean, I'll sort of let this be a call out, more generally to those of us who, work on, numerical relativity infrastructures. It would be nice if we developed them with the potential application in mind being to use them as a component as well within a larger framework of multiple infrastructures, et cetera. I'll tell you, I've had a lot of experience. One thing I didn't mention in my talk was the fact that within Black Holes at Home, we actually use the Einstein Toolkit to do horizon diagnostics because it has great horizon diagnostic software. But the way we have to pass information into the toolkit is really horrible. We basically output a data file containing a Cartesian grid within space-time data. Then we run the Einstein Toolkit from Black Holes at Home. It loads up the data. It runs the H-Finder Direct on the data and quasi-local measures, and then outputs the data. So transferring information between these infrastructures is really a pain. It'd be nice if, moving forward, we didn't have to do that. And then we could use these amazing, sort of meta architectures like HPX, like Charm++, to really drive a true multi-physics, multi-infrastructure approach to doing numerical relativity.
Thanks, Zach. Eric? You're muted, Eric.
Thank you. It was a cool talk. Yeah, fiddling with the buttons here. So you concentrated on CPU programming in your talk, but of course these days GPU programming is all the rage. And what you didn't mention is whenever you launch a kernel on a GPU, it runs in the background and the CPU runs ahead, and then you need to wait for the kernel to conclude, and you launch multiple kernels and multiple streams. And we are doing that with CarpetX and the Einstein Toolkit. So all that concurrency and parallelism, that you don't need HPX to suffer from that. We are suffering from that already because we're using CUDA. And the way you schedule grid functions need to take that into account. And currently we haphazardly shoehorn some device sync all, everything very expensive calls in there to make sure everything works. But we need a better story there in the Einstein Toolkit with CUDA. And we don't need HPX or OpenMP or something to begin to suffer.
Well, okay, so what you're saying is CUDA is already sort of a many-task framework by itself, and you already have to fight with it. And yes, that's certainly true. It would be nice if we had one many-task system to fight with, maybe, but yeah, that would the less complication, the better. But as you say, we are currently dealing with a significant amount already.
Well, everyone gets
Any other questions?
I have another one.
Oh, well, okay. Get to you next. Yes.
Okay, you're pointing away from me, but I think
I'm
you're
sorry.
pointing at me.
I'm actually pointing at you, but whatever.
Yeah, you need to point at the camera, not the screen, to point at me. Okay, yeah.
Where's the camera? Oh,
we're using MPI. Can HPX? Oh, now someone's pointing at me. Can we replace MPI by HPX? Does it do that thing?
Yeah. So you can, in principle, do that. HPX was intended to be something that you could use to orchestrate a distributed calculation as an MPI alternative. Of course, the joke of it is, right, depending on how you set up HPX, it might be using MPI underneath, but it would be a different interface to doing the distributed calculation. Yes.
Oh, that's fine. But if we all use HPX with MPI underneath, then Zach's code and the Einstein Toolkit can both use HPX and MPI underneath.
Right. Yes.
Just want to clarify on the detection of race condition. Sorry, the race.
Yeah.
I mentioned. So you mentioned that sometimes the variable, the results is that the variables are changed, that isn't necessary past the code.
Right.
So how do you detect those if it's just if you don't know that the results are actually?
Yeah, well, so it could be, right, that you have race conditions living in your code and they're subtly changing your results and you just don't know.
Yeah.
You don't know.
Oh, so-
That's, I mean, that's part of the reason why they're so terrible, right? Is because, you know, until we have a good way of detecting them and or preventing them in the first place, you may just have those problems and you may not be aware of it.
So you said like running something for a week and then happen once.
Yes, it could happen that way.
So like, it's very possible for if we make the document simulations, it would happen, and we don't know there's a fair machine.
Yes, I worked at a software company for a while, and we had a code with a race condition in it. And we knew that we had a race condition somewhere. And the customer, you know, every like month or so, we'd get a call from the customer that said, hey, this thing happened. And they say, you know, give us your logs, run again with this kind of logging enabled, because we didn't know where it was. And we never found it, at least not while I was there. You know, it was just so rare that it happened. And we tried to keep building more and more diagnostic information so that when it happened, we'd have a chance at figuring out what was causing it. But we never did, at least, as I said, during my tenure.
All right, Bruno has a question.
Bruno, yes.
Yes, just a curiosity. I wanted to know if you have already in mind some routines in the Einstein toolkit that could particularly benefit of this. I mean, in my mind, I had in mind maybe the con2prim routines, maybe that could have some idle cycles, but I don't know if you have in mind some particular routines that can benefit from this.
I don't. So the question was whether I have some routines in mind that benefit from this. I don't have anything at the current time. I'm sure there are plenty of things. Roland?
Yeah, I think I might answer part of Bruno's question, or Eric might. Eric actually did experiment at one point with using some sort of path-based parallelism for the communication. That would then let you, in principle, even overlap some of the communication with calculation, but also let you do the communication without having to do one group of variable after the next, and incurring the overhead of having to wait for that group to finish. That you just do all the communication with the system, and it handles them as quickly as possible. That was for that one particular case. It wasn't even computation here, but it was communication that we wanted to parallelize and avoid latency by taking communication through the system. Very good.
Bruno, did you hear Roland's answer?
Yeah, so what Roland was saying is there was an experiment that Eric constructed some years ago, which I'm not sure what actually became of it. But the idea was you could do the calculation on the interior of a region while the ghost zones were synchronizing, and get some overlap between the communication of the ghost zones and the computation in the central region. So that's a possible place where that could be used.
Okay, thanks.
Any other questions? All right, let's thank the speaker again.